We're now going to talk about the asymptotic properties of the standard linear regression estimator, the ordinary least squares estimator. In this case, we're going to assume a random design that our x's, our features, are random, and we're going to show that the ordinary least squares estimator is asymptotically linear and calculate its influence function. We're going to use this to show that the ordinary least squares estimator is consistent and when suitably centered and scaled, has an asymptotic normal distribution with a variance that we can calculate. So let's begin with our setup. Here we imagine we have n pairs of observations, xi, yi. Xi are our features, yi is our outcome, and these are drawn from some distribution f on Rp plus 1. We're imagining here we have p features, right? P may be 1 or p may be greater than 1, and a single continuous outcome. Now, we're going to imagine in this case that linearity holds, that our outcome is a linear combination of our features plus a mean zero error that has bounded variance. In addition, we will assume that this error is independent of our x's. We're not assuming that these errors are normally distributed. That's not necessary for the theory of linear regression. Here, we want to learn about these coefficients beta 1 up to beta p. One can also engage with parallel theory where we don't actually imagine that we have a true linear relationship between our outcome and our features. However, we are trying to make inference on the population line of best fit, or population linear function of best fit. That's not the route that we're going to take here. It's not that much more complicated, but there are a few more details. The most common estimator that we use in this case is called the least squares estimator. Here we choose estimates of parameters beta naught up to beta p to minimize the average square distance between our outcome and our predictions. You can think of the square difference between the outcome and the predictions as a loss function, and we are trying to identify the best predictive model that's a linear combination of the features to minimize that average loss over the observations. This is known as the least squares estimator. This idea is generalized in machine learning and in statistics in things like generalized linear models. We will cover those later in another video. One reason that this estimator is nice and commonly used is that there are methods which can compute it very efficiently. This is often called the objective function that we are trying to minimize, and it's common to rewrite this objective function in sort of a matrix vector notation. Here, beta is now a p-vector of parameters or coefficients. X is an n by p design matrix where each row corresponds to an observation, each column to a feature, and the ijth entry is the jth feature measured on the ith observation. And y is now an n by 1 vector of our outcomes stacked together. One might note that I've sort of dropped this beta naught when moving down to this matrix vector notation. We can do that because we might imagine that the first column of x is actually a column of all ones, and the first entry of beta is actually the entry corresponding to the intercept. In that case, beta would be a p plus 1 vector, and x would have p plus 1 columns, again with the first column that's entirely ones. So these two problems are equivalent, and we are often interested in understanding the behavior of beta hat as an estimator of that true underlying generative beta. This formulation is nice not only because it's compact, but because some simple matrix calculus can give us a closed form for that estimator. This follows pretty cleanly. This function, the 2 norms squared of y minus x beta, is a smooth convex function, so the minimum will occur where the gradient is 0. Now, if we take the gradient of this and set it equal to 0, we get negative 2 x transpose y minus x beta hat equals 0, that beta hat has to satisfy this. If we multiply this out, we get negative x transpose y plus x transpose x beta hat equals 0. And now, if we move this to the other side and solve for beta hat, we get exactly beta hat equals x transpose x inverse x transpose y, giving us the result down here. This presupposes that x transpose x is invertible, In the case that it isn't, there will be an infinite number of vectors that minimize this objective function, and beta hat won't be well defined. In general, that's not the case unless you have a funny situation where features are collinear. So now we have this nice form for our estimator beta hat. We would like to understand its asymptotic behavior. We would maybe like to look at the difference between beta hat and that true vector of coefficients beta. And ideally, we would like to show this converges to 0 in probability. We'd like to understand the rate that it converges to 0, and we'd like to know what happens if we scale up by that rate. And we can get all of that, in fact, if we can show that beta hat is an asymptotically linear estimator of beta and just identify its influence function. So that's the path that we're going to take. So for the first step, right, recall in the original definition, we had a y right here. We just substitute in y equals x beta plus epsilon, where epsilon is now a vector of our errors. So it's all of those epsilon values stacked on top of each other. This just follows from our original assumption of linearity. And now if we multiply this out, we see that the first term, we get cancellation between this, and we just get a beta. And then the second term just has an epsilon. We can subtract this beta over to the other side, and we get that this difference actually has a very nice compact form. X transpose X inverse times X transpose epsilon. Now, it's actually going to be convenient to move away from this matrix notation back to sort of a vector form where we engage with IID observations. The other thing I'm going to do is I'm going to put a 1 over n in here, invert it, and put another 1 over n out here. So there's going to be a 1 over n associated with this term and a 1 over n associated with the inside of this term. And we find this piece becomes this, and this piece becomes this. Now, this looks quite nice, though these might be a little hard to work with as, you know, xi transpose is a matrix, epsi epsilon is a vector. Nonetheless, we do have an empirical average of IID terms here with a smooth transformation applied to it. The matrix inverse is a smooth transformation. And similarly, we have an empirical average of IID observations over here. So what I would love to do for asymptotic linearity is part of me would love to take this piece, this is just a matrix based on all the observations, and I'd like to move it in here and call it part of the influence function. However, I can't really do that because this is based on all of the observations. What I'm going to do instead is I'm going to take the thing that this converges to. So I'll say this converges to something that I'm going to call sigma x, and then when I apply the inverse, the continuous mapping theorem will tell me that this inverse converges to sigma x inverse. So again, sigma x here is just going to be the expectation of each of these. And I'm going to take this sigma x inverse and I'm going to move that in here. And then I'm going to have an additional term which involves the difference between sigma x inverse and this thing multiplied by this piece. So I'm doing all of that down here. So I take sigma x inverse, right? I swap this piece with the sigma x inverse and I sub it in here. And then I have an additional term, which is the difference between this piece and that thing I was saying it converged to, sigma x inverse. So take a second to digest that. Again, this is just algebra. If you multiply this out, you will get this piece cancels with this piece, and this piece is exactly equal to what we have up there. Now, why do we care about this? Well, this is an empirical average of IID observations. So we know that this converges to 0 at a rate of n to the negative 1/2. Now, this is also an empirical average of IID observations, with ignoring this inverse for a second. So this piece converges to sigma x at a rate of n to the negative 1/2. And now, if we apply a continuous and differentiable map to both our empirical average and our limit, we know that that rate of convergence is maintained. One could use the delta method for that, or a quantitative form of the continuous mapping theorem, which we've seen in a previous video. So this piece is also OP n to the negative 1/2. And that might be a little confusing. So it might behoove you to work that out. We actually don't even really need that this is OPn to the negative 1/2. We really only need that this is little OP1, that it converges to 0 in probability. So now when we multiply this piece by this piece, something that converges to 0 at a rate of n to the negative 1/2, times something that at least converges to 0 in probability, we're going to get that this whole product is now little OP n to the negative 1/2. So all of that work here was basically to say this is going to be a remainder term. We don't have to care about this really ugly thing. And instead, all we have to do is care about this, our empirical average of IID terms. All right, so simplifying that down, what we have is beta hat minus beta is an empirical average of IID mean 0 terms, plus something that converges to 0 at a rate faster than n to the negative 1/2. And it's not hard to show that these terms are mean 0. Epsilon I is assumed to be independent of our xi's, and epsilon I itself is mean 0. So that gives it to us right there. So again, we have that beta hat is actually an asymptotically linear estimator of beta with an influence function that we can write in terms of x and epsilon, or if we're a little uncomfortable with this epsilon, we feel like the influence function should be a function of x and y, we can rewrite epsilon as y minus x transpose beta. So again, maybe this is the cleanest way to write the influence function. I'm abusing notation here a little bit, and in this case, rather than x being our design matrix and y being our vector of outcomes, x is just the set of features from a single observation and y is a single outcome. Now, we're going to be interested in the asymptotic variance of beta hat, and to engage with that, we're going to look at the variance of our influence function. So we can just directly plug in for our influence function here. Now, sigma x inverse is a constant matrix, and in fact, it's symmetric, so we can just take it out and left and right multiply the remaining quantity by it. Now, this next part's a little tricky. To calculate this, we use the law of total variance. So the variance of x times epsilon is equal to the expected variance of x epsilon given x plus the variance of the expectation of x epsilon given x. Now, because epsilon is mean 0, this is going to be 0 for every x, so the variance will be 0, so this term is gone. And here, once we condition on x, we can treat this as a constant and take it out, although again, we have to left and right multiply by this and its transpose. So we get the expectation of x variance of epsilon given x, x transpose. Now we note that epsilon and x are independent, so this piece becomes sigma squared epsilon, we can take that out, and this piece becomes the expectation of x transpose, which is exactly sigma x. So this becomes sigma squared epsilon, sigma x. So that gives us this piece. We now get cancellation, and we get this final result that the variance of the influence function is sigma squared epsilon times the sigma x inverse. So from here, we get this classical result, which says if we look at beta hat minus beta and scale it up by square root of n, that will converge in distribution to a normal with mean 0 and covariance matrix, that is the variance of the error times the inverse of this matrix that can kind of be thought of as the uncentered covariance matrix of the features. Now, if we wanted to use this for statistical testing or forming a confidence interval, we would need some sort of plug-in estimate for these two. And for that, we might use this empirical estimate that we already used in calculating beta hat, which is just this gram matrix involving our design matrix x scaled by 1 over n. And similarly, for the variance of the errors, what we might do is look at yi minus xi transpose beta hat. So this is sort of like epsilon I hat. We could think of it in that way. And then we're just taking the square sum of these. And rather than dividing by n, it's common to divide by n minus p. Although if we divide by n asymptotically, we would get the same thing, assuming here that p is fixed. So just a few notes. It's common that people claim you need errors to have a Gaussian distribution in order for regression to work, or inference from regression to work. That's not the case. We don't need the epsilon I to have a Gaussian distribution. All of those results relied on the central limit theorem and asymptotic linearity, not exact Gaussianity of anything. Here, we also engaged with random x. We assumed our features were random. There's an alternative approach that engages with x as a fixed quantity. It's a little bit trickier, and when you talk about things asymptotically, you still need to understand how x gets larger as n grows, and if x isn't random, then you have to put some funny restrictions on that. And finally, we assumed this population linearity, that y was a linear combination of the x's plus some independent mean zero error epsilon. But you can show actually a similar result if population linearity doesn't hold. And there, your target of inference, rather than being these generative beta parameters, are just betas that are defined as the population linear function or line of best fit, which may not be a great fit. So, there's a question on whether those are meaningful parameters to draw inference on. But regardless, we can still draw inference, and the theory still holds.